Hello friends, welcome to lecture 8.1. So, we are into the first lecture on the exciting topic of discrete wavelet transforms. In this lecture, we shall look at the definition of discrete wavelet transform, learn and review some basics of frame theory as relevant to the DWT, and then look at the theory of orthonormal dyadic DWT. Again, fairly an introductory lecture, and this lecture is primarily going to be theoretical. So, you will see a bit of math, but then mathematics is inevitable in this subject. Gradually, as we did in CWT, we shall look at a few applications, MATLAB based demonstrations and so on. So, before we plunge into the definition of DWT, we shall ask why we should be looking at DWT. Is it different from CWT and so on? Well, first of all, the CWT is a highly redundant representation. We have mentioned this quite a few times in the lectures on continuous wavelet transform. What we mean by redundant is it computes many more coefficients than necessary. As is what we are doing with a wavelet transform or even with short time Fourier transform is we are transforming a one dimensional signal into a two dimensional plane. So, obviously, we are generating more numbers than necessary, but it is possible that even in the two dimensional plane we can come up with a number of coefficients that is not more than the number of coefficients or the numbers that we had in the one dimensional plane. What CWT does is that in the two dimensional plane it uses many more numbers than necessary to represent the signal, and that is what we mean by redundancy. Now, when it comes to applications such as signal compression or energy decomposition across scales and other types of analysis, normally one desires a compact representation. What we mean by compact again is just the minimum number of coefficients that are necessary in the two dimensional plane, and this minimum intuitively cannot be smaller to begin with than the number of coefficients or the numbers that we had in the one dimensional signal. But in signal compression, once we have this minimum representation, we throw away quite a lot and we retain quite a few to achieve very minimal representations or even compressed representations, and we will talk about that in signal compression. So, the main question that often arises is when I am computing CWT, anyway I am going to discretize my scale and translation. We have seen that many times in computation of CWT and so on. Now, what is the difference here? We are saying in discrete wavelet transform, we have also mentioned this earlier, that it is nothing but CWT evaluated at specific scales and translations. In the computation of CWT as well, we are evaluating CWT on a grid of scales and translations. So, what is the difference now? The difference is in how we choose this grid for the scales and translations. In the computation of CWT, we choose an arbitrary grid. The user has the complete freedom to compute the CWT at as many scales as possible, as the restriction is only the computational power, but otherwise I can compute CWT over a very fine grid. In DWT, the user does not have a choice, and mathematically upfront we restrict our evaluation of CWT on specific scales and translations such that something is achieved. And what is that something? Minimal representation. We want to have as many few coefficients as possible in the two dimensional plane or the time frequency plane and still not lose information to begin with. So, that is the prime difference between CWT and DWT, and just this one difference opens the door to a very exciting world of transforms. It is not a new transform. Discrete wavelet transform does take birth from CWT, but because of the way we evaluate the CWT at the specific scales and translations, we achieve some very nice properties for the representation that are useful in signal compression, energy calculations, multi-resolution approximation and so on, and that is what makes it very exciting. So, let us now look at the definition of DWT. Again, we know that DWT is a CWT evaluated at specific scales. Now, what kind of scales are we looking at? Exponential scales, a naught raised to m, where m is an integer and a naught is a number that I am free to choose. And also at specific translations, here n b naught times a naught to the m. Now, you can quickly recognize a naught to the m is nothing but the scale itself. This n b naught essentially says I am moving the wavelet window in the analysis of the signal proportional to the scale of the wavelet. Remember, scale determines the width of the wavelet. If I am looking at large scales, high scales, then the wavelet is wide, and therefore, I should be taking large steps, whereas when I look at finer scales, lower scales, then the wavelet window is narrow. So, I should be taking smaller steps. So, let me just show you graphically on the board what is the qualitative difference between CWT and DWT. So, let us say this is the time, and here we have, let us say, the time scale plane, if you like it. Then at lower scale, so remember, unlike the regular time frequency plane, here we are drawing the time scale plane. Let us assume that this is scale 1 just for our reference, or let us say this is scale 0 and here we have scale 1. So, here we have S greater than 1, which means I have wide wavelets relative to 1, and here I have S less than 1. So, narrow width in time, right. So, what kind of wavelets do I see if I pick a certain scale here and I were to draw the wavelet, let us say it is going to be this wide. Whereas, if I pick a scale here, a wavelet centered at the origin could look this wide. So, it is all qualitative sketch. So, do not try to quantitatively compare the widths. Just to tell you, here you have narrow and wide relative to what you would see at S equals 1. So, maybe at S equals 1 you have, right. All of these wavelets are normalized to unit energy. What we are doing in CWT is we are marching ahead in time in with an arbitrary step size, and also we are choosing wavelets that are spaced in an arbitrary way in scales. That is, I choose a scale here, let us say 0.5, and then I could choose a scale, let us say 0.51, depending on how fine a grid I want on the scales. Now, in DWT what we are doing is, we are not really going to, at any scale we are not going to march ahead in time over an arbitrary step size, but we are going to choose a step size proportional to the width of the wavelet. That is the prime difference. So, if I look at this wavelet, I would choose the next time interval, that is where I should place the center here. The center could be somewhere here. So, that approximately, in fact, for a certain choice of A naught and B naught, I will have non-overlapping, I would have generated non-overlapping wavelet window. So, it is possible that in DWT also these wavelets can overlap. So, my next center would be here. So, this step size that I see here, the marching step size, and the next one here, let us say next center is here. This here is proportional to the width, and you can show a similar thing here. Here I would probably place, so here is the center of the wavelet to begin with. The next center could be somewhere here, okay, qualitatively it would be this far. So, you can see that wide wavelets are taking larger steps. It is like a long person be able to take long steps ahead, and a person who is short is actually taking more frequent steps. So, that is about it. So, it is a way you grid, you choose your grid points for the scale, and dWt, and that is with respect to the translation, and scaling is also a naught to the m. It is not a linear discretization, it is exponential discretization. Of course, normally you see a naught equals 2 and b naught equals 1 being the very common choice, but we will come to that. At the moment we are studying a more general problem. The rest of the story is the same, t of m comma n. So, now we have thrown away tau and s and we have replaced them with m and n. The only difference you should notice is we have reversed the order of indices here. When we were looking at CWT, we wrote t of tau comma s. So, time translation parameter appeared first and scaling parameter appeared next, but here we have m comma n, where m denotes the scale and n denotes the translation. So, that is generally the convention in DWT, but you are most welcome to choose your own convention. On the right hand side you see the familiar wavelet transform. In fact, in almost all DWTs you will never use complex wavelets. So, you can really throw away this complex conjugate here on top of the psi, and these wavelets are nothing but again children of the mother wave evaluated at specific scales and translations. Do not forget that we have a normalization factor to ensure that the wavelet has the same energy as the mother wave itself. So, an important point to keep in mind, which often leads to a lot of confusion, is that the term discrete refers to the discretization of the scales and the translation parameter, not the signal itself. If you notice in equation 1, the signal is still continuous, it is not discrete yet. We will look at a discrete time version of this integral in 1 when we talk about computation of DWT and practical aspects and so on. At this moment we will keep the signal continuous. Now, the question the big question that we have in front of us is, can I choose a naught and b naught arbitrarily? Is it possible? Well, this is where the frame theory, which was developed in computer vision by a couple of researchers, comes to our rescue. The frame theory was developed in computer vision, in fact in signal processing, where one was interested in knowing whether it is possible to recover a signal from its irregularly sampled version. So, signal is being evaluated at some irregular samples. Is it possible to evaluate the reconstruct the signal from its irregularly sampled version? So, that is in signal processing, those are the origins. Those irregular samples of a signal, you can think of the projection of the continuous time signal onto some functions, and therefore, frame theory essentially asks or addresses this problem of expanding any vector or a function like which has finite energy or 2 norm onto another family of vectors. So, I take a signal and I break it up into some components, and what frame theory tells me is whether breaking this up will yield a stable or a redundant or an orthonormal or a tight representation and so on. So, what kind of representation do I get when I take a signal and break it up into pieces, and how am I breaking it up? With the help of these functions. So, I project the signal in onto some functions. We do not call this as basis functions in frames yet, because we do not know if these functions are linearly independent or not. They are just some set of functions and we will look at an example to understand this. There are some set of functions, and what I would like to know is about the representation and also recovery of the function from these projections. Now, projections are often computed as inner products. Projections are nothing but shadows, right? So, every projection of a signal onto some function will get me some component of it, not the entire thing. So, what frame theory tells me is also whether I can recover the function from the inner products or the projection coefficients. Now, this n subscript n here, I am sorry if there is a confusion, this n unfortunately coincides with the n that we had in DWT, but please keep them disparate, separate. This n falls out of some integer set, and this set could be finite or infinite. What this means is essentially is that the functions onto which, or the vectors onto which I am projecting the signal of interest could be finite or infinite, that is all. Now, let us look at the frame theory a bit formally. First, let us learn what a frame is. Before we look at equation 3, I have written bold face here that a frame is a generalization of the concept of basis. We all know that any signal or any vector can be represented as a linear combination of some basis for that signal. But if you recall, the definition of basis requires linear independence. Of course, orthonormality is very nice, but linear independence is the minimum requirement for basis. What if I have functions that are not linearly independent? Then what do? That means I cannot expand the function, the signal onto these so-called analyzing functions. I can, and that is what frame theory essentially does. But then you can't really expand the signal onto any set of functions and expect that your broken up components are going to be stable or enough, or that you can recover exactly. So, now let us look at the definition 3. What constitutes a frame? What set of functions constitute a frame? A frame is a nice term. If you can relate this to the construction of a room or a house, if you have visited the construction, at the time of construction you see that there are some frames holding the roof that is being constructed, or some walls that are being constructed depending on what kind of wall you are constructing and so on. So, these are the supporting frames. You need a minimum set of supporting frames. You can have more than that, but you cannot have less than that. If you have less than the necessary supporting frames, the wall or the roof is going to fall down. So, it is not a stable set of frames. So, if you draw that analogy here, I have a set of functions which I call as a frame in a Hilbert space. Now, Hilbert space should not scare you. All that means is that I am working with a set of signals and functions that have inner products defined for them, and a norm is also defined for them. That is very important because we are dealing with signals that have energy, and some mathematical support has to be there to be able to say that energy can be calculated for this signal. So, a sequence of functions, whether this could be finite or infinite set of functions, is called a frame if and only if there exist two constants a and b such that both are greater than 0, but b is greater than or equal to a, such that the energy of the broken up components, that is how you view the modulus of the inner product of f with gamma n square. So, the term that I am summing up is the energy of the individual broken up component, and I put together that is the overall energy of the broken up pieces. If I compute the overall energy the way we are doing here, it should remain bounded between this lower bound and upper bound, and the lower bound and upper bound are themselves proportional to the energy of the signal. Clearly, it is possible that a and b can be 1. If a and b are equal and equal to 1, that means the energy of the broken up composition exactly matches the energy of the function itself. Now, we shall ask different situations, we shall examine quickly different possibilities. Obviously, a and b are both greater than 0, and we will also assume that the gamma n's that I have been normalized to have finite energy. So, the first frame that we have is a redundant frame when a is greater than 1. What does a greater than 1 mean? If you go back to this inequality here, obviously it means that the energy of the components put together is much greater or is greater than the energy of the signal itself. A is greater than 1, b could be anything, but that is a is a lower bound. So, which means I have more components than necessary, right. So, that is why the term redundancy comes in. Now, when a and b are at the most 1, they could be equal, both can be equal, but a is never greater than 1 and b is also never greater than 1, but then b can be greater than a, then we have what are known as linearly independent, we have what is known as a linearly independent frame. Why is it linearly independent? Why not perfect tight frame? Because a is not equal to b necessarily. when A equals B, we have a tight frame. What this means is that it is a very snug fit for the signal. You have really found you have really broken up the signal in a very tight manner. It does not mean that you have a minimal representation. That is very important. Okay. It just simply says A equals B. The lower and upper bounds are equal. When these lower and upper bounds are equal to 1, both, then we have an orthonormal basis where you have exactly the minimal set of gammas or the functions or the function frames to represent your signal f. And then we can say that we have a basis. In both situations, situation 2 and situation 4, we have gammas as basis, because in case 2 your frame is linearly independent. That means now I have a basis, and in frame 4 I have an orthonormal frame which is also linearly independent, therefore I have a basis. But in case 1 and 2 I do not have a basis, because linear independence is not being guaranteed. So these are the different possibilities that you can have. Now you can clearly see why frame is a generalization of the concept of basis. So let us look at a quick example here, and which I borrowed from Mallet's book. Suppose I am looking at the 2-dimensional Hilbert space, that is 2-dimensional real space where the inner products are defined, could be real or complex. And we know that these vectors E1 and E2, what are these E1 and E2? They constitute, they are this 1 0 0 1 orthonormal vectors. We know that they constitute an orthonormal basis. But instead of choosing E1 and E2, if I choose gamma 1, gamma 2 and gamma 3 as my new basis, I mean I do not want to call this basis as yet, but a new set of representing functions, then what kind of a frame do I get? Now it turns out that you get a tight frame with A equals B equals 3 by 2, and let us see why this is the case. So let us take any function in the 2-dimensional Hilbert space, and since E1s are the E1 and E2 are the basis, let us say assume that this function is a vector. E1 and E2 are both 2-dimensional vectors, and what I have there is gamma 1, gamma 2 and gamma 3. In order to determine what kind of a frame I have, I need to evaluate this summation. Right. So the inner product has to be evaluated, and here n runs from 1 to 3 because I have 3 functions in my frame. Sorry. What is gamma 1? Gamma 1 is E1 itself. Therefore, the inner product of f with E1, we know that E1 and E2 are orthonormal, which means the inner product between E1 and E2 is 0. So it is clearly by substituting for f here and applying the given information. What is the given information? It is orthonormal, which means the square 2 norm of E1 and E2 are both 1, and the inner product between E1 and E2 is 0. So this is the given information to us. So I just evaluate the inner product here, and what do I get? I get alpha 1, right. And then I have gamma 2 as minus 1 over 2 E1 plus root 3 over 2 E2. All right. So now I am going to evaluate the inner product of f with E2. What do I get? I have minus half E1 plus root 3 over 2 E2, sorry, should be gamma 1 and gamma 2, right. So I have here f, inner product of f with gamma 2, f is alpha 1 E1 plus alpha 2 E2, and therefore I have minus alpha 1 over 2 plus root 3 over 2 alpha 2, all right. And then finally the second one is fairly straightforward. once you have understood the second case. Gamma 3. So, I have here minus alpha 1 over 2 minus root 3 over 2 alpha 2. Now, all I have to do is I have to sum square these quantities, and what do I get? When I square this, I get alpha 1 square, and here I get alpha 1 square over 4, alpha 1 square over 4. So, when I add them up, I get alpha 1 square over 2. So, this summation here produces 3 alpha 1 square over 2, and then likewise here I have 3 by 4 alpha 2 square and 3 by 4 alpha 2 square. So, I get 3 by 2 alpha 2 square, then I have the cross terms which cancel out each other. This is nothing but 3 by 2 alpha 1 square plus alpha 2 square, and alpha 1 square plus alpha 2 square is nothing but the energy of f, right. So, this means essentially that the energy of f is alpha 1 square plus alpha 2 square. All you have to do is simply take the inner product of this with itself. Remember, the square 2 norm is nothing but inner product of any function with itself. By the property of E1 and E2, you can show this. So, this is nothing but 3 by 2, that is it. So, now you understand why we have a tight frame A equals B equals 3 by 2. So, what does this mean? Obviously, I mean this example, it is fairly obvious, it is a 2-dimensional space. I only need 2 basis functions to span the entire space, but I have 3 representing functions gamma 1, gamma 2, gamma 3 that have been constructed out of E1, E2, E3. Therefore, it is going to be redundant, and the only nice thing about this is it is a tight frame, right. So, tight frames have certain advantages, but we have redundancy. How much redundancy do I have? And that is what is measured by this factor A. Whenever you have a tight frame, A equals B, so the redundancy is measured by A. So, I have about a redundancy of 3 by 2. In fact, strictly speaking half, because when A equals 1, then I have minimal. So, that extra half is what is the measure of redundancy. It does not mean that I have a half function in excess, but it is just a measure of redundancy. Higher the value of A, more the redundancy that I have.